Next topic is meromorphic functions. So meromorphic function are those function which has a singular point, which has finite number of singular points. So that is called a meromorphic function, which is analytic at some points and finite number of singular point is called a meromorphic functions. Now, this is very important result, the number of poles and zero of a meromorphic function. Suppose f of z be analytic functions. So this is analytic function inside on a simple closed contour C except finite number of poles. It means it is a meromorphic function because it has finite number of poles or finite number of singularities. Let f of z is non-zero, then prove that 1 by 2 pi iota integration around C f dash z over fz dz, which is equal to n minus p. What is n? N is a number of zeros. And what is p? P is the number of poles. So remember here that if pole and or zero are of order s, then it is counted s times. For example, if 1 is the zero of the function with multiplicity 3, so it is counted as 3, not as a 1. So this is my theorem. So this is very important result to find this values, which is a 1 by 2 pi iota and equal to n minus p. Now this can be written as equation number 1. Suppose this is written as equation number 1. Now to prove this result, now this is the statement and the proof of the result. So prove this result. What is given part? So in the given part, so if I take this is as a proof. So what is the given part? In the given part, we have a simple closed contour. So this is a simple closed contour C, and at which the function is analytic except finite number of points. So first I take z is equal to a 1 1 0, and I will prove it for 1 0 and 1 pole. Suppose this point, this is some point z equal to a, so this is a 0 of a function, and this is some point z equal to b, which is a pole of a function fz. Now if I take, let z is equal to a, so what is this? Which is a 0 of a function f of z with multiplicity n. Suppose it is a 0 of a function with multiplicity order, also we can say that of order n, this values. And similarly z equal to b, which is a pole of fz of order, I can take it as m. So it is a pole of order m and it is a pole of order, if I write it is a pole of order p. Suppose it is a pole of order p. Now here I take 1 0 with multiplicity with order n and 1 pole with multiplicity with order p. So remember, first of all I take only 1. Now if I draw a circle inside this C around A, so it is a neighborhood of A and it is a neighborhood of B. So this is a neighborhood of A and this is a neighborhood of B. So this can be written as C and N. So this is Cn and this can be written as C of rho. So this is written as C of rho or C of P. Also we may write the another name. So this is equal to this values. So C of N and C of, if I take, so it is a C of P. So this is a circle. Cn and Cp are non-overlapping circle inside C with center Z equal to A and Z equal to B respectively. So what is Cn and Cp? So Ca and Cp. So here what is, so I write Cn. So first is Cn and second is Cp. So what is this? These are non-overlapping circles with center inside C with center Z equal to A and Z equal to B respectively. So I write in this way respectively. So I take two circles. One is circle of center A and second is circle of center B, and then these are the non-overlapping circle inside the C. Now what is my claim? So here I want to prove my result for a 1 0 with multiplicity n and one pole with multiplicity small p. So this can be written as my claim 1 by 2 pi iota around C f dash z over fz, which is equal to dz, which is equal to n minus p. So this is a for one pole and one zero. So it may be extended to the number of zero and number of poles, number of finite zero and number of finite poles. Now by extension of Cauchy theorem, as we know that since Cn and Cp are the circle inside the C, so this 1 by 2 pi iota around C, this is some function f dash z over fz into dz, and this can be written as 1 by 2 pi iota integration around Cn f dash z over fz into dz, and this is plus 1 by 2 pi iota integration Cp, and this is again f dash z over fz into dz. So this is equation number 4. So this is by extension of Cauchy theorem. So this result is by extension of Cauchy theorem. Extension of Cauchy theorem. So must write it in this way. This is the extension of Cauchy theorem. So by applying extension of Cauchy theorem. Now since z equal to b, so what is z equal to b? So it is a pole of function fz of order p. So with multiplicity p, the of order p. Then how we can find the residue of this function? So then f of z can be written as phi of z over z minus b raised to power p. Now this phi of z is a analytic and non-zero within Cp, because this is a pole of order p, so it implies this phi of z is analytic and non-zero inside the circle Cp, because in the Cp z equal to b is the pole of order, z equal to b is the only pole of order p. So this phi z we can write in this way. Now taking logarithm on both sides, so what we get, now this is, if I can write this is as equation number 5. So taking logarithm log of f of z, this values, which is equal to log of phi of z minus, this is log of this, so this can be written as p time log of z minus b. So here I am using the property of a logarithm, so this can be written as in this way. Now if I differentiate this equation with respect to z, so I will get my integration. So this can be written as differentiate this equation, differentiate with respect to z. So what we get f dash z over f of z into dz from this, and here this value is again phi dash z over phi of z into dz, and here minus p and derivative which is z minus b into derivative of z which is equal to 1. So this get this values. Now integrating on both side with respect to the around Cp. So this is a Cp and this integration is Cp and this integration is around Cp. This is dz. So integrating with respect to this values. So here it is differentiate, then integrating this will respect to this. Now this function phi z, which is analytic in the circle Cp, if it is analytic in the circle Cp, then its derivative is also analytic. So this total function is analytic in the Cp. Then by Cauchy theorem, the integration around Cp is equal to 0. So what is the reason? Reason is this function is this total function which is analytic within and on a circle Cp. By Cauchy theorem, this integration is equal to 0. Now what is this? This is minus p. Now what is the integration of dz by z minus b? So this is equal to 2 pi iota. So we know that. So this is 2 pi iota, this integration. So if it is 2 pi iota into total, it is 2 pi iota into b. So we get these values. Now from this it implies what we get? We get 1 by 2 pi iota integration Cp f dash z into dz over f of z, which is equal to minus small p. So this is the equation number 6 ja 7. So from this I get this values 1 by 2 pi iota integration around Cp. Now in the second part, my aim is to find the integration around Cn. Again we know that z is equal to a. So what is z equal to a? So this is a zero of function fz with order which is equal to order n. So it means this function f of z, this function can be written as z minus a raised to power n into psi of z. So psi of z, also psi of a is a non-zero. Also psi of a is a non-zero. So this values. Now this psi of z, which is analytic function inside and on a circle Cn, within and on a circle Cn, right? So this is analytic within and on a circle Cn. So again on similar way, so first I taking the logarithm of this function, then differentiate, then integrate. So log of f of z, this is equal to log of psi of z, this values, and minus n times logarithm of z minus a. Now next step, differentiate. So differentiate this equation with respect to z. So this value is f dash z over fz, and this value is equal to psi dash z over psi z, and this value is minus n over z minus a. Now integrate this function with respect to dz, this function with respect to dz, and this function with respect to dz around the circle Cn, Cn and Cn. Now multiply by 1 by 2 pi iota on both sides. So 2 pi iota, and here 1 by 2 pi iota, this values. So this value is equal to, now again psi z is a analytic function in the analytic function inside Cn, then by Cauchy-Gauss theorem this integration is 0. Now here, which is minus 1 by 2 pi iota, so into n. So what is the integration of this z minus a? So which is equal to 2 pi iota. So this is a 2 pi iota integration, this cancel. So total term is equal to minus n. Now here I get the integration around Cn, and here I get the integration around the circle Cn. If I write this equation as equation number 8. Now this equation and equation number 8 and equation number 7 and 8, this used just substitute in equation number 4. So this is equation number 8 and 7. So this is what I get. So equation number 7 and 8. So substituting the simply using equation 7 and 8 in equation number 4. So what we get? We get 1 by 2 pi iota integration C f dash z over f of z into dz, which is equal to small n minus small p. So this is my result. Now this is for a one pole and one zero. If I have a finite pole and finite zero, so that is a meromorphic function. Now suppose in that case, suppose a function f of z, it has poles, it has pole z equal to bm of order pm. So remember this, it is a pole of order pm where m is running from 1, 2 and so on up to r. So it means fz has a pole which is b1, b2 and so on up to br. So what is the order of b1, which is p1, and this is a p2 and this is a pr. So these are the order of this pole. Similarly, we can take the 0 and similarly f of z, which has 0 zeros, z is equal to a, this is bm, so the br, this we can write it as br. So here it is a n of order small n, and this is, if I write here at, suppose it is at, so this is nt where t is running from 1, 2 and so on up to s. So what it means? It means it has 0, a1, a2, a3, so it has 0, a1, a2 and zeros are a1, a2, as, this is up to as, or its order is n1, n2, n3 and ns. So this is a order of this term, this values. Now enclose each pole and zero by non-overlapping circle within C. Now if we have this kind of situation, then enclose each poles and zeros by non-overlapping circle within C. Then the equation become 1 by 2 pi iota, this is around C, f dash z over fz into dz. So this is equal to summation of n s. So nt, where t is running from 1 to s, minus summation of pr, where r is running from pm, where m is running from 1 to r. So this value. So what is the first sum? This is treated as capital N. What is the second sum, which is treated as capital P? So what is this? It is a number of zeros. It is a number of zero of the function fz. And what is this summation, which is a number of pole of the our, this is a number of the pole of the function f of z. So what is n? So n is summation of nt, t is running from 1 to s. So what is this? It is a number of zeros of function fz. So what is p? Capital P. So what is capital P? So this is a, from m is running from 1 to r, pm. So what is, this is a number of poles of fz. So which prove our result, that is related to number of zero and pole of a meromorphic function. So this result is very important for a principle of argument. So in the next lecture, we will discuss the principle of argument.